We gotta find an alpha, a positive constant alpha. We gotta find an interval. I mean, well, the interval, this interval is going to be the x naught minus h, right? X naught plus h. Now what's given, what's not given here? We don't know the h yet. We don't know the alpha yet. X naught is given to us, right? But that's it. Now we're going to apply the operator t in 12. So the t, well, I think the t would be g, yeah? So apply theorem 2. Yes, I believe we're basically setting g equal to t, if you like. Right, we're going to try to show that t is a contraction. Now t, how is t defined? T of y, remember, is equal to, the same as we had over on the other board, why not? Well, fine. Why not plus the integral from, what was it? X naught to x.
F of x, or f of t, y of t.
T, y, oh thanks, y of t, dt. Our goal is to show this particular, I mean that defines t of y, right? We want to show that that is a contraction if we choose our constants appropriately. So he says first choose positive constants h1 and alpha 1 such that what? So it's pretty typical analysis proof. He starts by making a suboptimal choice and then explains how you can take that and refine it into the choice we actually want. So let's kind of try to follow along here. R1 is equal to what? It's equal to xy such that the absolute value of x minus x naught is less than or equal to h1, and the absolute value of y minus y naught is less than or equal to alpha 1, right? That's got to be a subset of the rectangle we were given to start with, right? The rectangle we were given to start with is where we know we have continuity of the f and the partial derivative of f with respect to y, which define the given differential equation. So then what? So that what? What has he done here? What's the nature of these choices? I mean, he says, I mean, I guess nothing really, except that the difference between R1 and R is that R is I mean, we can draw a picture. It's probably good to draw a picture. Here's R, right? Right, this point down here is what, A comma B, A comma C rather. This point over here would be like B comma D. And then what?
It's an open rectangle, but R1's going to be closed.
Yes, R1 is a closed rectangle is the main thing, I think. Oh, thanks. So R1, and R1 is also symmetric about the point x naught and y naught. So like it's a little bit more than that. So wherever the point is, like x naught and y naught, this rectangle R1 is like if I could do it, I mean this is the center of the rectangle, right? It's within, and that makes sense. If that's an open rectangle, wherever the point is, x naught, y naught in it, you can certainly form a closed rectangle that's within the open rectangle and like that. That makes sense that you can do that. I'll buy it. Sure, why not? I'm not going to pay a lot for it though. All right, so then what? Well, closed rectangles are awesome because if we have continuous functions on closed sets, we can use the extreme value theorem, right? So there exists constants. There exists an m greater than 0 and an L greater than 0, such that x and y in R1 implies what? First of all, the absolute value of f of xy is less than or equal to m, and the derivative, partial f partial y, at the point xy, is less than or equal to L. And the only reason I can do that is because I'm assuming partial f partial y is continuous. All right. What is next? So let g be a continuous function. Where's g in all this? What is g? G be a.
They're defining it now, right?
Let g be a continuous function on I1 that satisfies g of x minus y not less than or equal to alpha 1 for x in I1. For such a g, oh, I guess now he's suggesting, well, but, I mean, I guess you can consider such a g, right? He's saying a continuous function. So the I1 is what? It's equal to x naught minus h1, x naught plus h1. So yeah, surely we can consider g a continuous function on that interval. I mean, okay, fine. I mean, that's fair enough. And you could consider it, and you could also consider, suppose it satisfies the condition absolute value of g of x minus y naught is less than or equal to alpha 1. I mean, I guess you could do that. You'd be doing what then? I think you'd be looking at one that's within alpha 1 units of y naught, right? You're looking at a function which is relatively close to the y naught function, right? Over this interval I1. Because the max, right, like the max of this won't be more than, all right. Anyway, for such a g, we have the following. T g of x is equal to y naught plus the integral from x naught to x. Okay, I mean, that's just definition of the t, right? So far, so good. We got it. And then what he wants to do is he wants to look at the absolute value of t of g of x minus y naught. Well, that's the absolute value of the integral from x naught to x, f of t, comma, g of t, dt. All right? Great. And now using properties of inequality, properties of absolute value and definite integrals, we can trade this. This is less than or equal to what? Less than or equal to the integral from x naught to x of the absolute value of f of t, g of t dt, right? Let me put some color on here. It's just bound and determined to roll off that in. See here. Thank you. So then what? Oh, well, we know that for such x as we're considering here,
F is going to be bounded.
yeah, that this is, you can look up here, this guy, right? So we can trade that's less than or equal to m times the integral from x naught to x of dt, I suppose. Yeah. And I should really put the, oh, I guess I messed up. Oh, I'm a dummy. I should have left these guys out here too. So that would give me these. And that would give me m times x minus x naught. Okay. he says, from a geometric point of view, we have shown that if the function g satisfies g of x minus y naught less than or equal to alpha 1 for x and I1, the graph of the function t of g must lie in the sectors bounded by the lines y equals y naught plus or minus m times x minus x naught. See the figure? I'm afraid to see the figure. Alright, fine, let's see the figure. Where's G in this picture? I don't know if I can recreate this picture worth anything. I will attempt. Got like these lines, and through the middle we've got y naught. So, and then the top, this one is y equals to y naught plus m times x minus x naught. And down here we've got y is equal to y naught minus m times x minus x naught down here. And what else? We got a couple rectangles going on in here. Big one goes out to what? This is, oh no, that's not the dotted one. Sorry. The undotted line is what? It's x naught plus h1. Then over here you'd have x naught minus h1. The whole rectangle is r1. That's this thing up there. And then he has y naught plus or minus alpha 1. That's the top and the like this is y naught plus alpha 1. This is y naught minus alpha 1, those horizontal lines. Right? He doesn't, where's G in all this? That's the thing he hasn't graphed. Maybe he just didn't graph G because he thought it would be too busy.
But T of G is there.
Yeah, but what is G?
It's just some function in that rectangle.
So, is it, where does it map, where does, what's the out, I guess G, what is G is a, are they the continuous functions, these functions, do they have to map, where does G map to is my question.
Well, I mean, it's defined on like I1 and then it maps to...
I guess my real question is, are these continuous functions from I to I? Or are they just are these continuous functions from I to the reals? I thought they were just from I to the reals. Like, I don't remember, assuming...
Well, it's from I to G minus y naught. It's like the alpha...
Oh, right. That condition right here is so important. Thank you. Yeah, I should not ignore this. This tells me graphically what G looks like, doesn't it?
Right.
So that means that the distance from G to y naught is less than alpha 1, which means...
It could be anything that right now.
Yeah, G could basically look like whatever. That could be G. But what T of G looks like is not up for grabs. T of G has to do what? It has to fit. He's like, T of G has to be... Where does T of G have to go? It has to lie in the sector between the lines with slopes plus or minus m. So T of G has to somehow... So this green line might be the T of G. Because we've shown that T, because and that I mean, this is just, there's nothing profound I'm saying. Now that I write it all out and digest it, I have no indigestion. I'm fine. So this, the distance between tg of x and y naught, in other words, the output of the graph of t of g, the value of the function tg at x is smaller than the value of this function. Well, that is exactly, that and it's relative to y naught, of course. So this is exactly like, I can make this into this minus y naught absolute value, which is just that. So yeah, the green functions between the asymptotes, so to speak, here. Okay, then what does he do? He's defined some dotted lines in here. I haven't made this picture, but have you zoomed in on that picture?
Oh, I don't know how to zoom.
Oh, okay. That's probably okay. I'll just... zoom out a little bit. There we go. Let me zoom out. Zoom back out here. It's cool. I think it... Anyway, it's cool. Now, but he then defines... He puts some dotted lines on this picture. Right, what is the significance of those dotted lines? Sorry.
It's like H2 instead of H1.
Yeah, this is x naught plus H2. It's very busy. X naught minus H2. What is the significance of those ones? So he says H2 is equal to, run out of room. So H2 is the minimum of H1 and alpha 1 over m, right?
Mm-hmm.
And he says you also want to make H less than 1 over L. So basically you're gonna choose H such that 0 less than, I mean, you could just say choose H such that this and go on with your life and it would be the same. He's just trying to he's trying to motivate why you do this. H1 alpha 1 over M1, and he got sick of the motivation, so he just said, and you also need 1 over L, by the way. You'll see that later. Okay, enough motivation. I'll also slap 1 over L in there for our convenience. All right, now we're going to let that. So finally, we have worked our way to the appropriate definition for I and H, all right? I'd really like to erase all this. I guess I should probably continue over here. If I was smarter, I would have written the theorem over here and worked around. But as you know, I don't make good choices. All right, let's see here. Ooh, that was probably a mistake. Oh well. So it's like, okay, fine. So we'll let H equal, again, the minimum of what was it? H1 alpha 1 over M and 1 over L. All right, and you let S equal to G in the continuous functions on I, such that the norm of G minus y naught is less than alpha, or equal to it, where alpha is equal to alpha 1, and we have I equal to the interval x naught minus h to x naught plus h. All right. All right, now we can finally see if T is indeed a contraction map. Let's do it. So here we go. So first of all, does T maps S into S? He says clearly T of gx is a continuous function. Well, what is T of gx? Let me just write that again so we have it in front of us. T of gx is what it's equal to y naught plus the integral from x naught to x f of t, g of t, right? dt. So he says clearly T is, well, I mean, I don't know. Oh, sorry. I mean, we're trying to show this is actually the case. This much is true. Certainly the output is a continuous function because you're, I mean, how do we know that this defines a continuous function? Well, the dependence on, it's an integral, right? So by the, it's in the fundamental theorem of calculus, I think, that the integral, I mean the area function, the continuity of the area function. I mean, you get differentiability of the area function, so go figure. Okay, so, anyway, so.
It's 5 o'clock p.m.
I gotta get out, I gotta pick up space. Okay, so, I don't wanna, we need to finish this. So check it out, the norm of, the absolute value rather, T of g of x minus y naught, right, is less than or equal to m times x minus x naught. We proved that. Prove that over here already. I was pointing at the other board, Jess. Use your imagination. Now, so this is of course less than or equal to mh. Do you see why?
Because it's an interval.
Right.
X naught minus
Exactly. Right. It's because of the x. We should say x is an element of I. And then how was h constructed? Well, h was the minimum of these guys, right? So I can play the game that this is less than m times alpha 1 over m. Well, isn't that convenient? Isn't that convenient? And that is, of course, equal to alpha 1. Hence, the norm of the function t of g minus y naught is less than alpha 1. And that means that t of g is an element of S, right? Because that's how we defined S. And then contraction is more fun. To show it's a contraction, remember we have, okay, so look at this. We look at the norm of t of u. What are the u and the v?
Functions on S, or in S.
Right, okay, so we're supposing here that x is an element of I and that u and v are elements of S. He has threatened to use the mean value theorem. Let us count the ways. Alright, so this, if you look at that, what happens with the y naughts? They cancel, right? You get the difference of integrals. So you might as well just write it as one integral. The absolute value of the integral from x naught to x of f of t comma u of t, right, minus f of t comma v of t dt. Close absolute value. Then, do you see what he's saying? So that's the change. You notice that the x component of f is fixed. The y component is going from u of t to v of t. So you're looking at the difference of f with x fixed with y changing. So the mean value theorem says that the instantaneous rate of, that the average rate of change in y is matched by the instantaneous rate of change in y, holding x fixed. That's the partial derivative of f with respect to y. So we're using the mean value theorem in the next step as it applies to the y partial derivative. But remember that the partial derivative is just an ordinary derivative, so holding one of the other things fixed anyway, so there it is. Alright, so partial f partial y at t comma z of t, where z of t is what?
A function between u and v.
Right, exactly. So we're And I suppose we're not, how many times are we using the mean value theorem here? Like, how many times have we applied the mean value theorem?
Once. I mean, did we do it before? Or are you talking about this specific example?
Well, I would say that we're applying it once for each t.
Yeah.
So, infinitely many times. Okay. Right, because you're doing it at each t. But I can do that because I have continuity of partial f, partial y. Means like, anyway. And then what?
We have a bound on partial f, partial y.
Ah, right. This is less than or equal to L, s value integral from x naught to x, of u of t minus v of t, right? So he's like, okay, so of course that is, and then do you guys understand the next step? I'm not sure I understand the next step here. He says this is less than or equal to L times the norm of u minus v over the interval, of course, times the absolute value of x1 minus x naught. And then he's like, okay, so that's, and the step that follows after it, I understand. Of course, that's LH, norm of u minus v. Okay, great. So he says, okay, so you can set k equals to LH, and then k equals to LH, and we're done. That shows it's a contraction.
Well, I think it makes sense to think about it geometrically, because they're saying if you look at the largest difference between the two functions, and you just take that constant function from x naught to x, that's going to be greater than or equal to the actual integral of the difference between the two functions, because you're taking the maximum of that.
So basically, your argument is just that I can take this integral and say that that's less than or equal to the integral of that guy.
Right.
Yeah. But then you've got absolute values going on. So of course that's just equal to x minus x naught. Okay, yeah, I gotcha. Take the absolute value, got that. And then that's a contraction mapping. And therefore, what we got? Well, it now follows from the Banach fixed point theorem that t has a unique fixed point in S. And so the initial value problem 10 has a unique solution in S. Moreover, the solution is the limit of the sequence of successive approximations defined in 13. Now there's a little bit more fine point, like you said. To complete the proof, we need to resolve one subtle important point. That is that while we've shown there's a unique solution in S, we've not shown that every solution to the initial value problem on the closed interval x naught plus or minus h must lie in S. To see this, he says, look at a solution and recall that f is bounded on M in the rectangle R1 that we drew over there. Since u of x naught is equal to y naught, the graph of u of x must lie in R1 for x near x naught. So for such values of x, we have that the value of the defining equation of the differential equation f of x comma u of x is less than or equal to m. And so the derivative u prime is equal to that, is less than or equal to m. So therefore, for x near x naught, the graph u equal to t of u must lie in the shaded sector that I put the green graph in earlier, and I didn't shade it. In fact, the graph of u cannot escape from the sector x minus x naught less than or equal to h, which is, by the way, less than or equal to h2, because this would require that the absolute value of u prime of x equal to the f of x comma u of x greater than m at some point in the sector. Hence, u of x minus y naught is less than or equal to alpha 1 for all x minus x naught less than or equal to h, that is u is in S. And then I think then that would mean that it also converges to the same solution, because we have that if it starts in S, it converges to the same thing. So if there was conceivably another solution, the Picard iteration would say it has to be the same solution, because something like that. I'm not 100% on this last paragraph, but
Yeah, it's saying that if it's a solution, then it's an S.
And then, so on the next page, same theorem, but for systems of ODEs. And I suppose that one would actually be more like what we did in Edwards, but basically the same proof holds. Now, if you go ahead here, you know, in the next section he basically, you know, existence of linear solutions. So basically his proof, well, actually this isn't linear just yet. He first has this theorem on continuation of solution. Basically, if you have a certain condition, you can continue solutions as he describes here. Yeah, let's see if I was trying to get to. I think these arguments are quite easy to follow after you've looked at what we've looked at together, if you want to study more about this stuff. Let's see, the existence and uniqueness theorem for linear systems on page 851. He's like, suppose you've got a n by n matrix function, a of t, and vector function, f of t, continuous on open interval a to b. It contains the point t naught. Then for any choice of initial vector x dot, there exists a unique solution on the whole interval a to b to the initial value problem x prime equals a of t, x of t, plus f of t. All right? And his proof of that, right, he's like, you pick a closed subinterval, any closed subinterval you like of a comma b, right? And you let g of xt equal to a times x plus f. That's continuous on the closed rectangle. And the partial derivative of that with respect to the ith column is just the, well, with respect to the ith variable, that ends up just being the ith column of the matrix. We know that we've seen that kind of thing advanced. But if the matrix is continuous, then the partial derivative with respect to xi is continuous, of course. And, of course, then you can bound it, which means then you can use the continuation of solutions theorem that I just glossed over. And there exists then a unique solution on the closed interval a tilde to b tilde, but that being an arbitrary, interval, you have a unique solution on the whole interval a to b. But then you can do reduction of order to just as well get the unique solution to a nth order system, as he describes right there. So basically, once you understand the proof of the one we went over today, it's just a hop and a skip and a jump to prove the corresponding theorem for systems. Then you prove this continuation theorem, and then you can get all your favorite nth order in systems with continuous coefficients. And then finally, over here in the next section, he starts to look at the sort of more deep issue of continuous dependence of solutions, talking about a specific, he talks about specific estimate, this sensitivity to initial conditions. Like if you have the same differential equation and you change initial conditions a little bit, how much do your solutions change? Do they stay close together or not? We actually have some theorems in this section which kind of quantify that. Or on the other hand, if you have the same initial point and you change the differential equation a little bit, do you get the same solution? So sort of sensitivity to model variation versus sensitivity to initial data. There's theorems in this section on that. And again, it's all built over the Banach fixed point theorem. So, what do you think? Should I cover this stuff in DiffyQ next semester if I get a chance?
Do like a bonus lecture.
Bonus lecture. What I should do is anybody who comes to me, I want to do an honors project, I'm like, okay, chapter 13. I've had people try to do the chapter 12 before, which is the Sturm-Liouville theorem stuff, but they're not very successful. They don't really penetrate it that deeply. They don't get very far into it at all. It's tough. But I love the way analysis is presented in this chapter. I think it is a wonderful example of how analysis should be presented and discussed. You don't get buried in the. It really focuses on what's important without like getting distracted by the Weierstrass test or something. Using tools to prove things, as opposed to proving everything from epsilonics. I think the structure of these arguments is very nice. I think. Anyway, you can study more if you want, but I just want to show you that much, and so I think I've shown you enough. And we will next time go to the other world of weirder stuff. Yes. Next time we will begin our search for kryptonite.